Hello, I'm very excited to talk about the work that I've been doing at Stanford. My research interest is in mobile visual search, and in the past 2 years, I've been focusing on how we can use visual text information for visual search. Here, the text I meant is the text and images. Let's start by showing a short example of a mobile visual search application. Here, a user uses a mobile phone to take a picture of a city that he's interested in. Then, query data is sent to a server for recognition. Once a match is found, the identity of the match is returned back to the user, along with other information such as description, pricing, and in this case, music samples. What's happening in the background is what we call the back of visual words-based matching. From the image, we would extract interest points at different locations and scale within the image. Then, from these interest points, we would extract a local image patch and calculate the descriptors from the local image patch. Then, when we want to match it against a large image database, we only need to do is compare the extracted descriptors with the descriptors pre-extracted from the database images. This approach is in fact pretty powerful. We could use it for CD and DVD cover recognition, as we have just shown. We could use it for location recognition by matching images of building facades. We could also use it for product recognition, provided that there are good textures on the labels. We could use it for book spines, but in this case, we need to first segment out the book spines. And this approach is also the back end of many streaming augmented reality systems. One thing we notice, however, is that the performance of the system drops when we are dealing with images that consist mostly of text, such as with dealing with text in the book spines. To understand why, we'll show a toy example of detecting interest points in text images. What we typically use to detect interest points within images are blob detectors. Shown here is a Laplacian-Gaussian-based blob detector. When we detect interest points, we use this to filter the image to find responses that are extremas. Now, if we give it an image that is a text image as shown here, and the size of the Laplacian-Gaussian filter corresponds well to the stroke width of the text, what we would get is actually a high response on the character regions within the image. And when we detect extremas, we find that the extremas are at the endpoints of the strokes and the dots on I's and J. The filter is doing a good job. However, the interest points detected is at a very local scale, and the descriptors extracted from these interest points are fairly repetitive, and this becomes a problem for the retrieval pipeline. This motivated us to look into the approach of using text. In this case, given the query image, we will first detect the text within the image, then from the detected regions, extract the word patch and send the word patch into the OCR for recognition. This would give us the recognized text for each patch. Then, when we want to perform search, we can simply use text-based search to search through the document database. However, the problem with this approach is that there's an optical character recognition engine inside. For OCR engines, if you give it a well-posed image, you would get good results. However, if the input image has a bit of variation, such as a picture taken using the camera phone, the accuracy begins to drop. When you use images that are handwritten, who knows what the character recognition engine will give you? This motivated us towards an approach that does not use OCRs, but use word patch descriptors. On this end, we developed a new type of descriptor called WordHOGs, which stands for Word Histogram of Oriented Gradients. In this approach, from the detected text regions, we extract the word patch. From the word patches, extract a WordHOG descriptor. Then when we want to match it to a large database, we use the WordHOGs to perform matching. Different from the OCR-based approach is that we can deal with a wider range of images. We can deal with texts that are more graphical, where character recognition engines would not be able to recognize. Here we'll refer to images that consist mostly of text as dense text images, and images that contain both text and graphical components as sparse text images. Lastly, to make this system a practical system, we also studied how we can implement the system. The image database is typically large, so it's placed on a remote server. So we looked into how we can compress these features before sending these features to the server for recognition. My research contributions have also been on these 4 different blocks within the system. For visual text detection, I have developed a bottom-up text detection algorithm that is based on maximally stable extremal regions. It's a multiple orientation text algorithm that can detect text reliably. To describe the visual text, I developed a new WordHOG descriptor. I have found that it can perform very well for large-scale word-patch matching. I also investigated how to compress the WordHOG descriptors and also how to compress location information of image features and develop the location histogram coding technique. Finally, I used the developed sub-blocks to build an image retrieval pipeline using WordHOGs. I also developed a random sampling scheme to reduce the database size. I will show that it can be used for both dense text and sparse text images. For the talk today, in the interest of time, I will focus on visual text detection, word-patch descriptor extraction, and matching with word-patch descriptors. But before talking about what I do, let's briefly look at what other people have done. In essence, what we're trying to do is perform image retrieval with visual text information. If we look at the type of images these algorithms are dealing with, we can classify them based on whether they are dealing with dense text or sparse text images. We can also classify algorithms based on how well they know the text they are dealing with. At the lowest level are image features, where they are agnostic of whether there's text within the scene. For dense text images, people have generated geometric invariant features that is based on locations of words within the image. On a high level are character shape features, where they look at the number of holes, ascenders, descenders of characters. And at the highest level are algorithms that use OCR to recognize the text. For sparse text images, people have developed retrieval algorithms that uses SIFT descriptors extracted from character locations, or simply using OCR to recognize the text directly, however, at lower accuracy. What we will show is that our pipeline will be able to work with both types of images at a very good performance. To build up an image retrieval system, we need 2 essential building blocks. The first is the visual text detection block. Visual text detection was first developed for scanned documents. In this case, they only needed to deal with extracting the text from a white background. In our case, we're detecting text in natural images, which is a much more complex problem. There will be a lot more background clutter, while the text is just a small portion within the scene. People first tackle the problem using a texture-based approach. From a sliding window that goes through the image, they extracted different types of features, such as Gabor, color histograms, and trained a classifier to determine whether there's text within the sliding window. More recently, however, people have started looking to a region-based approach, where they use stroke-width transforms, image segmentations, or stable extremal regions to find regions within an image that might correspond to character candidates. Then, from these character candidates, we build up text lines and words. The second block we need is the word-patch descriptors. Word-patch descriptors tries to solve the following problem. Given a query word patch and a database of word patches, we want to find a word patch from the database that matches with the query word patch. The idea was proposed in 1996 by Manmetha as an alternative solution to character recognition. He coined the term word spotting. He used binary images and performed template-based matching. Others follow the approach and generate features such as projection profiles and density features from the binary image. However, with binarization, you lose some information. Thus, people have started looking into using information directly from the image itself, such as using image grading features. We'll come back to these methods later in the talk. Now, let's take a look at how visual text is detected. We developed a bottom-up text detection algorithm. Given an image, we first perform character candidate generation to find regions within the image that might be text. Then, from these character candidates, we look to pair them together based on their geometric information. Finally, we find text lines from the connected sets of characters and try to separate the words. In the first stage, given an image, we first extract the maximally stable extremal regions. This would give us regions within the image that would correspond to characters, but also regions that do not. To rule out these false regions, we use a series of tests on the shape information. For each region, we extract several shape information. One important information is the stroke width transform, which gives us the stroke width values for each pixel within the region. From this, we can generate tests such as stroke width variations within the region to rule out false regions. We also look at the contour reflections. If there are too many contour reflections, it's typically too complex a shape to be text. We also check the number of holes within its region and use the minimum enclosing circle to estimate the size of the characters, which we then check with the stroke width. And also the shape moments to check the major and minor axes to see if it's just a long line. Once the character candidates passes through these tests, we go on to the second stage. In the second stage, for each character candidate, we look in 16 different directions and try to pair them together. For each pair, we look at their character size, stroke widths, aspect ratios, and projected distance. Characters on a text line will be of similar font, and these properties will be similar. Then, we go on to the next step of filtering these pairwise connections. For each character, we generate a distance inverse weighted orientation histogram that uses the direction of the connections and the distance of the connections. Then, we use the maximum value to generate a threshold to rule out the others. We could see that the shortest distance connection is kept. This helps us to rule out cross text line connections. Finally, in the last stage, we form the text lines. From connected sets of character candidates, we pick two characters to form a straight line. We would then attach other characters onto the line based on the distance. We do this exhaustively for a set and pick the text line that yields the most characters. For this case, it will first give us mysteries, which is of 9 characters, and then Ellery, which is of 6, and finally Queen, which is of 5. Then we go on to the filtering at the text line level. We check for repeating characters and whether the characters are just most solid characters and the aspect ratios of the characters. Once the text line passes these tests, we try to separate the words based on the character spacing. To show the performance of our algorithm, we use 2 data sets to evaluate it. Shown here are some example images from the ICTAR 2011 text detection competition dataset. We could see that there's a wide range of font and distortions. These images come with labeled ground truth text boxes, as we shown here in red. Our detection results are shown in green. We could see our text detection algorithm works well for the top 2 rows of images. However, we miss cases shown in the last row where there's a lot of clutter on the text itself and where the color of the text is actually the same as the background. The second data set we tested with is the oriented scene text detection dataset. For this dataset, we could see there are text in almost every direction. Similarly, we have the ground truth labeled in red polygons, and our detection results shown in the green boxes. We could see we could detect text in almost every orientation. However, we miss cases where there's glare on the text and where characters are formed by small dots and not actually a single region. For this dataset, we show the quantitative comparisons with other approaches. Shown on the left are the 3 best performing algorithms reported in the literature, where ours is on the right. You can see that the precision of our algorithm is slightly lower than the best approach, but our recall is higher than theirs. If we look at the F-score, we could see that the performance is similar. Now that we have described how we detect text in words, let's now talk about how the WordHOG descriptors are used. As we have mentioned, the WordHOG descriptors is designed to search and find a matching database WordHOG given a query WordHOG. We tried several different methods that are based on image gradient information. First, proposed to extract SIFT descriptors from every character location. This requires character segmentation, which sometimes work and sometimes don't, and generates a very few amount of features. Tsai, on the other hand, proposed to extract HOG features from subblocks within the WordHOG, and he used a slit of HOG features to perform matching. He used dynamic time warping to compare pairs of WordHOGs. Yalnis proposed to extract interest points on the WordHOG itself, but as mentioned, it would generate repetitive key points and it would require an additional stage of interest point detection. Thus, we ended up developing our own descriptor called WordHOGs, which stands for Word Histogram of Oriented Gradients. Similar to Terasawa's approach, we extracted HOG from subblocks within an image, but we divided the square blocks into narrower subblocks. From each subblock, we would calculate the image gradients, generate the histogram, and generate the HOG features. Then, starting from the top left, we go from top to bottom and left to right to concatenate the HOG features within the WordHOG to generate the WordHOG descriptor. We could see easily that the WordHOG descriptor is a variable length descriptor. The length of the descriptor depends on the width of the WordHOG. Since it's based on HOG features, we can compress it efficiently using type coding. And with its block structure, we can generate overlap SIFT descriptors from the WordHOG very easily. How do we generate the SIFT descriptors? Suppose we want to generate a SIFT from this location, and we need to calculate the SIFT descriptors from this spatial bin. Since we already have the HOG features from the underlying subblocks, we can simply just add up the HOG features up to generate the HOG features for that spatial bin. Similarly, we can generate the HOG features for the next spatial bin. We do this for every spatial bin to generate the full SIFT descriptor. Then we normalize it as we typically do for SIFT descriptors. Then we move one step to the right and generate a SIFT the same way, using HOG features from the new set of subblocks. We do this for every subblock step along the horizontal direction to generate a series of SIFT descriptors. One thing to note here, since we do not do trilinear interpolation or Gaussian weighting, it's a modified version of SIFT descriptor. But for convenience sake, I'll refer to the descriptor as SIFT for the rest of the talk. Now, how do we do WordHOG matching? Given a set of WordHOG images, we first perform WordHOG extraction. Using these WordHOGs, we generate the SIFT descriptors. And using the SIFT descriptors, we train a vocabulary tree-based matching pipeline. In the pipeline, each WordHOG would correspond to one database entry. Thus, given a query image, we would extract the WordHOGs, generate the SIFT descriptors, and use the descriptors to perform vocabulary tree-based matching. However, since we're dealing with text patches and that we generate descriptors on a single line, we would need to redesign the geometric vivification stage. We use the geometric vivification method as shown here. Given the feature sets of two word patches, we will first pair the nearest neighbor features together based on the descriptor distance. But because we're dealing with text, we use a distance threshold to rule out bad matches and try to keep multiple matches. To rule out the false positives, we search for the longest common sequence of matching feature pairs that preserves the order. This would help us rule out the crisscrosses as was shown in the connections. Finally, we use the locations of the matching feature pairs and fit a scale and offset model between the locations. For matching words, we know that they only differ in the horizontal line position, and hence we use the scale and offset model. To generate a single geometric score, we use the percentage of features that matched up for the two images and multiply the two numbers together. A detailed look of the word patch descriptor would reveal the following blocks. First, the box is bounded on the word. Then, anti-aliasing filter is applied before resizing the word patch. Pre-blurring of the word patch is applied before calculating the histogram of gradient features from the sub-blocks. And finally, the HOG features are coded using context-based type coding. In developing the WordHOGs, we trained for several different blocks. We'll look at the margin between the word and the box. We looked at how much pre-blurring is needed, and also how wide the sub-block should be. We also looked at what we should use for coding when we're coding the histogram of gradient features. For the vocabulary tree, we trained for the vocabulary tree depth and also the distance threshold used for the feature pairing stage. Once we have trained the system, we tested the performance using a 960,000 word patch database. It was generated using 400,000 different words with 3 different casings. We don't generate lower casings for names, so it's not 400 times 3. We use Arial fonts and generate words. Shown on the right are some examples of our database words. For testing, we printed words and took pictures of them and generated 1,000 queried word patches. Shown on the left is the recall of the rank list at 2 stages of the pipeline. We could see that the recall performance after vocabulary tree is not too well. We could imagine this as many words may be of the same set of characters, but just in different order. With geometric verification, we can enforce the order and rule out the ambiguities and improve the performance. Here we show comparisons with other approaches. Since we're working with word patches, we could use OCR to recognize the text. We show as reference in the black dashed line the performance of Tesseract, which is an open source OCR engine. It has a performance around 76%. For other schemes, we change the database size to test its performance. At the bottom is the character SIFT approach, where you extract a SIFT descriptor from every character location. Because of its small amount of features, the performance is not that well. Using fast interest points with SIFT descriptors, we can get a much better performance. However, as the database size grows, the performance drops quite a bit. Difference of Gaussian interest points with SIFT descriptors performs better than fast. However, the trend is similar. Our WordHOG performance is shown here. It's much better than other approaches. At a database size of 1 million, we have a performance of 84%, better than the OCR engine. Now, since we have talked about the 2 major building blocks, now let's look at how we can build the image retrieval pipeline. As we have mentioned, given a set of database images, we will first perform text detection to find the visual text locations within the images. Then, from these visual text locations, we extract the database WordHOGs. For each database WordHOG, we will know its origin database image. Then we use this database WordHOGs to train a WordHOG matching database. When a query comes in, we detect the text and extract the WordHOGs from detected text. Then we use each query WordHOG to query the WordHOG matching database. For each query WordHOG, we will get a list of matching results, which we can link back to its original database image. And we merge all the lists into one single list. However, we still need to make sure that the words are still in order. Hence, we use an image-level WordHOG-based geometric verification scheme to reorder the list. We will then finally return the ranked list back to the user. We note that here that the flow is very similar to text-based search, but for text we can find same words easily. For WordHOGs, it's not that easy because we have gradient features. So to prevent the WordHOG counts of the database to grow too large, we need to do duplicate WordHOG merging. In this case, we find similar WordHOGs and group them together. We would use one representative WordHOG for each set. When we merge scores, we simply pass the score for multiple documents instead of just one. But how do we find similar word patches? The most straightforward approach is to calculate the pairwise distance matrix. One thing to note is that we don't need to calculate the pairwise distance for every pair. For 5 duplicate WordHOGs, the least amount of pairwise comparisons we need to make is just 4. This leads us towards a random sampling approach. But the question is how much to sample the matrix? Well, the answer lies in random graph literatures. In one of the results, they derive the probability of a graph being fully connected given a certain number of edges. From this result, we can identify the number of edges we need and use the number to determine the rate which we should sample the matrix. Using the random sampling approach and by grouping similar length WordHOGs together, we can reduce the total computation amount by 3,000 times for a database size of 10 million WordHOGs. To test this approach, we use 2 different datasets. One is the dense text image dataset, which consists of 20,000 images gathered from conference proceedings and electronic books. We printed and took 350 images as query images. The other is the sparse text image dataset, which consists of 200,000 images of book covers gathered from the Open Library Archive. Similarly, we took query images of the text regions of the book covers and generate a query image set of 420 images. The first thing I would like to show is the size of the database WordHOGs. We show here the WordHOG sizes for different database sizes of the dense text image dataset. For dense text images, the number of WordHOGs in a page is around 500. So, with a database of 20,000 images, the number of WordHOGs is around 10 million. This would be a burden for the server. With duplicate WordHOG merging, we can reduce the size to a much smaller one. For the database of 20,000, we can reduce it from 10 million to just 2 million. Overall, we get a 5 times size reduction. And how does the retrieval perform? We test the retrieval performance for database sizes ranging from 1.25K to 20K. Shown at the bottom is the retrieval performance of SIFT descriptors. As mentioned previously, image features-based methods would break down. Much better is the text-based approach, where we use OCR engines to recognize the word patch and use it for text-based search. We get a very nice retrieval performance of above 90%. By using WordHOGs, we get a performance that's even better than text. For small databases, we get an almost perfect performance. For large database sizes, we get a mean average precision of over 95%. How does it perform for sparse text images? For this test, we varied the database size from 6 to 200,000. The performance of the WordHOGs for this dataset is also quite well. For a 6,000 database, it's around 95%. As the database size grows, the performance drops. At 200,000, it's still around 92%. How does image features perform in this case? SIFT descriptors does make a comeback and performs just as well as WordHOGs. But since we're using images of text, our approach would be much more efficient than SIFT. To show that, we look at the query size for two types of approaches. Shown on the graph is the performance of WordHOG features at different query sizes. WordHOG is a low bitrate image descriptor. At a query size of around 2,000, the mean average precision performance is close to 90%. If we use WordHOGs, we can get similar results, but using just a few hundred bytes. At the same retrieval performance, we can get a total size reduction of 8 times. And this brings us to the conclusions. My research is on exploring how we can use visual text for visual search. There's 3 blocks that I focused upon. The first is the visual text detection stage that finds visual text locations in images. We used a bottom-up text detection algorithm to find text. From the large amount of tests we use, we find a few key features that help in shaping our algorithm. First of all, maximally stable extremal regions are good character candidates for text that have a good contrast compared to the background. Then, stroke width information is very helpful information for pruning out false positives. Finally, using distance inverse weighted orientation histograms, we can rule out cross text line connections and also speed up the processing. For WordPatch descriptors, we have developed a new descriptor called WordHOGs, which stands for Word Histogram of Oriented Gradients. It's a histogram of oriented gradient based descriptor and can be compressed efficiently using type coding. Its overlap subblock structure enables fast SIFT descriptors generation. Using this approach, we find that the WordPatch matching performance is far better than other approaches and character recognition engines. Lastly, by combining the different blocks, we built an image retrieval pipeline that uses WordHOGs. It's an image retrieval engine that can work for both sparse and dense text images. For the pipeline, we also studied how we can reduce the database size by using random sampling. And we show that for images with visual text, using compressed WordHOGs to perform mobile visual search is a much more efficient solution than using compressed image features. Thank you.